Welcome to my presentation. Myself, Motiur Rahman, PhD student, Purdue University. The title of my paper is MIST, Medical Image Segmentation Transformer with Convolutional Attention Mixing Decoder. The outline of my presentation is introduction, problem statement, contributions, dataset descriptions, model workflows, results, and conclusions. Medical image segmentation is necessary to diagnose diseases, formulate treatment plans, and assess treatments. It is one of the essential steps for providing treatments through computer-aided systems. Precise segmentation also expedites diagnosis and improves cancer and tumor detection rates. Initially, the convolutional neural network, such as UNet, was found promising for medical image segmentation. Later, vision transformer and other transformer designed for computer vision was found promising also for medical image segmentation. Problem statements. Although a significant number of research have been carried out where they proposed different CNN-based models, different transformers, different CNN with self-attention, and CNN and transformer together to segment medical images. But they are not effective in capturing long and global features together. Also, for computing multi-head self-attention, they used linear projection, which is computationally expensive. In addition, the used attention mechanism is not enough effective to capture short and long dependencies of all pixels in all spatial dimensions. Hence, it is very important to address all these issues to improve medical image segmentation. Our major contributions. So our major contributions in this study are proposed a new decoder named as Convolutional Attention Mixing Decoder. We introduced an attention mixer that combines computed multi-head self-attention, spatial attention, and squeezed and excitation attention together. We used a convolutional projection instead of linear projections to compute self-attention. We also utilized deep and shallow voice convolutions in order to expand the model's kernel receptive field. So for this study, we have used two popular medical image segmentation dataset named as ACDC and Synapse dataset. The ACDC dataset has a total of 100 cases, which are divided into training set, validation set, and testing set. The Synapse dataset has a total of 30 abdominal CT scans and their corresponding segmentation mask, which are divided into training set and testing sets. So these divisions are followed by the suggestions of the dataset curator. Now, the model architecture. The figure shows the model architecture. So the left side is the encoder part where we have used pre-trained MaxViT model. The right side shows the decoder part, which has one bottleneck and 4 decoder blocks. The bottleneck operates similarly to the other 4 decoder blocks, except gathering more information in this channel by increasing the channel size twice while keeping the image size as same. And the final output is generated by combining feature maps from decoder blocks 2, 3, and 4. So how the decoder block operates will be shown in the next slide. The left figure here shows the architecture of each decoder block, and inside each decoder block it has deep voice convolution, shallow voice convolution, multi-head self-attention, spatial attention, a squeeze and excitation attention module. And the implementation of each module is shown in the right side. The figure in the top shows the implementation of deep voice convolution and shallow voice convolution, while picture in the bottom shows the attention mixing, so where we have mixed multi-head self-attention, spatial attention, squeeze and excitation attention together. This equation shows how each of the module is being implemented in Python. Now, model training. To train the model, we used combined dice loss and cross entropy loss, and the final loss function is the weighted combination of dice and cross entropy. We have trained the model for 300 epochs, and we used early stopping in order to tackle the model from the overfitting. The performance of the model has been evaluated based on the dice score and 95% of hash drop distance. The equation shows how we have implemented these two metrics in order to measure the performance of our model. Now, results. The table 1 shows the performance of our model over the ACDC dataset. So in this dataset, we have segmented left and right ventricle and myocardium. And according to the table, we have found that our model outperformed all other state-of-the-art models in terms of mean dice score. If we look at the individual segmentation score, then we have also found that our model has overpowered other state-of-the-art models also. Table 2 shows the comparative performance of our model over the Synapse dataset, where we have segmented aorta, gallbladder, right and left kidney, liver, pancreas, spleen, and stomach. According to the table, our model outperformed all other state-of-the-art models in terms of mean dice score and hash drop distance. And we have also found that our model segments individual organs more precisely compared to other state-of-the-art models. The bold row shows the performance of our MACE model. We have also performed an ablation study in order to find the optimal settings. Table 3 shows the comparative study where we have experimented the effects of interpolation on performance. And we have found that a bilinear interpolation returns the highest mean dice and hash drop distance. So that is why we have used bilinear interpolation for rest of the study. We have also performed different experiments in order to find the optimal settings for the model, where we have tested the effect of attention mixing, multi-head self-attention computation technique, number of dilations, and attention aggregation. And we have found that our model with attention mixing and multi-head self-attention with convolutional projection, dilated convolution with dilation 2-3, and attention aggregation with concatenation return the highest mean dice score as well as mean hash drop distance. This figure shows the quality of our segmented images. Here, the first row shows the ground truth and segmented images of ACDC dataset, and the bottom row shows the segmented and ground truth of Synapse dataset. So, and the first and third column shows the ground truth, while the second and fourth column shows the segmented images. And from this figure, it is clearly seen that the ground truth and segmented images are very close to each other. Now, conclusions. So from this study, we have found that attention mixing has a significant impact on performance. We have also found convolutional projected MSA, that means multi-head self-attention, reduce the computational cost significantly, as well as increase the performance. Dilated convolutions help to extract long-term dependency, and our MACE model outperformed all other state-of-the-art models, including the baselines. Thank you.